In this video, we're going to look at some examples of drawing resonance structures when we're given a particular molecule. What I have here is the cheat sheet from my last video on resonance structures, and these are the patterns that I'm going to be looking for when I'm trying to draw the resonance structures of each of these molecules, and I'll be referring back to each one of these particular patterns. All right, so we're given a molecule, and we want to draw the possible resonance structures for it, or the possible alternate resonance structures for it. And so one thing the book does, and so I've done the same thing here, is they didn't put the lone pairs in on the oxygens and the nitrogens, so we need to be sure that we do that. So they are given the formal charges, right? So if I have a neutral oxygen, it's going to have 2 bonds and 2 lone pairs. So I know that I have 2 lone pairs on that oxygen. And so the only pattern that I see that we have is we have a lone pair that's allylic to a double bond, right? And to be sure that we're in the right distance, remember the rule is 1, 2, 3. So when I start on the double bond, right, I've got 1, 2, 3, right? And so this is a 2-step. And so we're going to take one of our lone pairs, and it's going to form a double bond there. And then this double bond is going to form a lone pair on that carbon atom. And so the resonance structure that we're going to get right, so now we have a double bond here. We have just the single lone pair now on the oxygen. And I made a mistake here. That's not supposed to be an oxygen. That's just going to be my lone pair. Right, and now I've got to check that my formal charges in the new structure are correct. Right, so the oxygen went from having the lone pair to now sharing that lone pair. So it's going to go from neutral to positive. And then this carbon atom went from having to share those bonded electrons, now it gets them by itself. So it's going to go from neutral to negative. And I think that's the only resonance structure that we have for this particular molecule. Okay, here we have another example, and I think the pattern that I see in this case is I have a carbocation allylic to a double bond. Right, and again, the pattern I'm looking for is 1, 2, 3. So they're close enough to do it. So what's going to happen here is the double bond is going to move over there. This is just a 1-step, or a 1 arrow. All right, now my double bond is here. This guy didn't change. Right, and so this carbon atom went from having a positive charge, right? We added these bonding electrons, so it's going to go from positive to neutral, right? This guy, right, is losing a bond, but it's gaining a bond, so he's not going to change, right? But now this carbon atom is just losing those bonded electrons, so he's going to go from neutral, and now he has our positive charge. I think you can see we can do this again. And now my double bonds are there and there. This is the carbon that lost the bonded electron, so he gets the positive charge. And then that's as far as we can go. Right, I can't go again because now, right, if I tried to move it again, it'd be 1, 2, 3. Right, that's not where the positive charge is. So this positive charge is not allylic. Of course, I could go back the other way, but that's just going to get me the other resonance structures I've already drawn. Okay, here we have another example. And again, they're not putting the lone pairs on the nitrogen, so I should put those in. Right, and when nitrogen is negative, it has 2 bonds and 2 lone pairs. And so I think the pattern that I'm seeing now is I have an atom with a lone pair adjacent to a carbocation. And so these electrons are going to move down here. right? And now my nitrogen atom, right, essentially went from getting the lone pair by itself. Now it's got to share those lone pair, so it's going to go from negative to neutral, right? And my carbon was positive, right? But now it's gaining some bonded electrons, so it's going to go from positive to neutral. All right, again, we should put in our lone pairs. A neutral oxygen has 2 lone pairs. I think the only pattern that we have here is I have atoms connected by a pi bond that have different electronegativities. So we're going to move the pi electrons, put those on the oxygen. All right, now the oxygen went from sharing the electrons to getting in a lone pair, so it's going to go from neutral to negative. And the carbon is losing those bonding electrons, and so it's going to go from neutral to positive. All right, let's put our lone pairs in again. All right, so the first pattern I see is the same one that we had last time. I've got 2 atoms connected by a pi bond with different electronegativities, so I can move those electrons up to the oxygen. And that's going to give me that resonance structure. And now I have a carbocation allylic to a double bond. And so we can find another resonance structure by doing that. So now the double bond is there. Right, and then the one that lost the electron density was that one. Okay, in this case, again, they're not putting the lone pairs in, so we've got to figure those out, right? And when carbon has a negative charge, that means it's going to have a lone pair. All right, and so now I have a lone pair allylic to a double bond, right? Again, our pattern 1, 2, 3. And so I can move those guys down. This is the one that's a 2-step, or 2 arrows in the same step, I guess I should say. So now the double bond is here. The lone pair is here, right? And this carbon, it started out, it got to keep the lone pairs for itself. Now it's got to share them, so it loses the negative charge, right? This guy had been sharing the bonded electrons. Now he gets them by itself, so the negative charge has moved over there. All right, so I think I'm going to start this one off. Well, I guess I should start off by putting on our lone pairs. And one important thing to notice when we're doing these resonance structures is look for all the one arrow ones first. And the reason I say that is there are 2 things we could do here. We could do the 2 atoms connected by a pi bond with different electronegativities and move those guys up, or we could say, oh, hey, we have, right, a 1, 2, 3. We have a lone pair allylic to a double bond, but if I do that one first, I'll only get one other resonance structure. If I do this one first, we're going to find we get 2 additional resonance structures. So if we can do a 1-step before, rather than doing a 2-step, or 2-arrow, we want to do that. And so we're going to do this one first. If we don't do the 1-arrow first, then it's easy to miss some of the resonance structures. All right, and now I have a lone pair adjacent to a carbocation. So we'll do that. And the positive charge moves there. All right, just one more example. All right, so this one's kind of a doozy. There are a number of things that we can do here. Let's put in our lone pairs first. All right, and so I think, again, there are two things we could do here. I have a 1, 2, 3, so I have a lone pair allylic to a double bond, but that's one of the 2-arrow ones. I have a 1-arrow one where I have a carbocation allylic to a double bond, so I think I want to do this one first, otherwise I'm in danger of missing some of the resonance structures. All right, so now my double bond is here, and my positive charge will be on the one that lost electron density. All right, and now I can do another one step. So now I have another positive charge allylic to a double bond, so I can do this. All right, and the carbon that lost electron density is that one. And I think I can do it again, but I'm running out of room, so I'm going to go on to the next slide, but right, what we're going to do is that. Okay, so this is where we ended up last time, and I said what we're going to do is this. So now double bond is here. That carbon gets the positive charge. And then for our final one, now I have a lone pair adjacent to a carbocation. So I can do that. Now we have the double bond here, and the oxygen with 3 bonds and a lone pair picks up the positive charge. And so between the last slide and this one, we should have 5 different resonance structures for this molecule.